So what we're going to do now is we're going to use the ansatz that I presented in the last slide, and we're going to do some derivations. We're going to explicitly derive the WKB solutions, and we're going to analyze what they mean. So we had this following expression here, which was psi x a e I over h bar sx, which we said this is similar to that in the idealized case Vx equal constant. This was a statement that we made. And we're going to insert this into the time-independent Schrodinger equation. So let's have a look. We have, don't forget, h psi x equal e psi x. So the left-hand side is going to look like this. The right-hand side is going to look this can go, and we're going now to compute the left-hand side. So we need to have the second derivative of psi x. So let's compute d2 dx2 psi x. This is d2 dx2 a I over h bar sx. And we find, applying this derivation once, this dash here I used to simplify the notation, but in case you have forgotten, this is the dsx dx, and we're going to apply the derivation once more. So if we differentiate once more, you find this is a derivative of a product, right? This here on the right hand side of this equation. So you are going to find, you have first to apply on this guy and leave this alone, and then you differentiate this guy and leave this alone. So this is going to give you I h s double dash x minus s h bar square. And here I have pulled already this out. Okay, reminder as well, this is d2 sx dx, sorry, 2, okay? Just that we are clear about notation. But what we need now is we need to plug this back into the time-independent Schrodinger equation. And if you do that, you get minus IH2M S double dash X plus 1 over 2M S double dash X square. Sorry, the square is wrong. Make this smaller. And here you have AEI over H bar SX. Plus V, don't forget V. E H bar over S. E over I over H bar SX. And here we're going to have E, which is the energy, E I over H bar. Put the A also. Too many SX. Okay, so this bit is associated with the P square part over 2M, the kinetic energy part of your Hamiltonian. This is associated with your potential. Notice that the potential depends on X. And here is the right-hand side of the time-independent Schrodinger equation, which is dealing with the energy of the particle. So here is this guy. So this is, if you want to be more explicitly, this is minus H bar square over 2M d2 dx2 applied to psi x. Okay? So moving on, we find, so far there is no approximation, looks just more complicated. So we can say that our time-independent Schrodinger equation has become, just making it a bit nicer, okay? Minus H bar 2M S double dash X plus 1 over 2M S X square plus Vx minus energy is equal to 0. Okay, so we made the ansatz that we mentioned. We use that to rearrange the time-dependent Schrodinger equation, and we got something that looks a bit more complicated, but is going to be useful for the next derivations that we are going to perform. So what we have here then is we have a nonlinear second order differential equation. And in the limit, H bar going to 0, the solution is S dash X is going to be plus minus 2M Vx minus E. See, you already get something nice because you make H bar going to 0, and that's why sometimes the WKB approximation is also known as semi-classical approximation. Because when you take this limit, you can see there is a clear correspondence here of this derivation here, this derivative being the momentum, if you wish, of the particle, which we had postulated at the very beginning. So we can say that Sx is plus minus integral of Px dx, and I'm putting a constant here so that we have this in mind, where Px is square root of 2m Vx minus E. Let me check if I haven't forgotten anything. No, it looks okay. So taking h bar, this is important, taking h bar going to 0 is called semi-classical approximation, as it often allows to derive classical equations of motion from quantum expressions. Well, this is a deeper discussion. In fact, it's not only about classical equations of motion, but this is an important part of it. And you probably heard of WKB approximation being called semi-classical. And this is one of the reasons why, actually a very important reason why. And so far, just to bear in mind, this is something we have done, okay, just to find in the limit what x is. So far, in this equation here, this equation is exact, this one. We have not performed any approximation. We have not expanded on anything. We are just considering another way of writing the time-dependent Schrodinger equation. Okay, so what we need to bear in mind right now is what expansions we can do to get to an expression that is tractable for potentials that are smooth enough. Okay, so that's what we're going to do. So we're going to consider the expression. So we will consider the expansion as x is x0x plus h bar s1x plus h bar square s2x plus and so on and so forth. So what we're doing this is we're expanding powers of h bar. And this is again some educated expansion because we know what we get in the limit of h bar going to 0, that we have something that is in fact very intuitive and that we can relate to classical mechanics. So what we'll do next is we're going to insert into the time-independent Schrodinger equation, and this is going to give me Now, one way of writing this down, which is a bit nicer, is if I write these like j equals 0 to infinity h to the power j, h bar to the power j, s jx. So here I'm making it clear, I'm expanding in powers of h bar, but I want to have a notation that is a bit more compact than this guy. So I'm going to insert this in the time-dependent Schrodinger equation. And when we do this, we find minus IH2M. Remember, we had already expressions in terms of S, and we're going to have power to the sum over J, 0 to infinity. I'm not considering this. H, J, S, J, double dash X, plus, I'm putting this, but it's just the notation gets a bit charged, you know. 2M J 0 infinity H to the bar to the power J S J dash X plus Vx minus E equals 0. Okay, so we're going to look at terms which correspond to matching powers in H bar, and we're going to demand that they independently sum to 0. Expansion was 0, yeah. But this guy has already a H bar, right? Hang on. Yeah, this has a H bar. So if I put this from 0, I have to put plus 1 here. Or I have to shift this to 1. So 0th order, we're only getting contributions from here. Right? No, sorry. This guy is, but I can bring this inside and make like this. It also works. So to 0th order, we're going to find 1 over 2m as O. And this is something we have already considered when I showed you the limit of h bar going to 0. And this means then that if we rearrange this, dSOX gx is plus minus square root of 2m e minus vx square root. And to the first order, we'll find minus I 2m s double dash x plus 1m s1 x s0 x dash 0, which we can rearrange, we can cancel things out, so we can write this as minus ISO double dash x is equal, so I multiplied by m to get rid of this, multiplied by 2 to get rid of this. So and I brought part of the expression to the right-hand side. Now, we can write this as if we get rid of this minus and we put the -1, when we put the I to the right hand side, we can write this as S dash minus 2 I S1 dash X. Okay, so consider the expansion to first order, and we consider the expansion to 0th order. So let me write it here, 0 order, and here first order. And we know that this 0th order, let me write this because I just stopped here, that you can write SOX like this. Whereby this is what we call P of X. Just to make it clear, because what we're going to do is we're going to replace this guy. We're going to say this is also P dash X divided by PX, which is kind of very convenient for us. And if you look now at this expression, you can see that this is a natural logarithm. So we can say also that natural logarithm of, if you integrate, so this is derivative of natural logarithm, so that integrate left hand side, right hand side, right? So just chum, 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 all with regard to the x, dx, you're going to find that natural logarithm of px is equal to natural logarithm of SO dash x, which is then minus 2i S1x plus c, which is a constant, that's arbitrary. Anyway, second order, you can move on. You can do this up to whatever order you think is useful for you. So you have minus I S1 double dash S plus S1 square plus 2S plus 2S2 second order dash S0. I'm omitting the argument because I'm a bit fed up, but you have X everywhere. Let me make it nicer. Okay. And there is an explicit expression in Joachim as well. Just write the expression, I'm not going to compute it. If you want to know it, have a look there because you find. Just now, just occurred to me that this x dash here is just indicating a change in dummy variable. This is nothing related to differentiation. Here I used it as well. I'm just mentioning that because it was a bit unfortunate that I used the same symbol, but it's not. You can see from the context, okay? So let me put just to make it clear. Dummy variable. And here you have this going up to x. Same. Okay? So this, you can find this expression, see, if you're curious, see Brunsden and Joachim. And what is important for us here is that S2 will vanish for dv dx sufficiently small. As long as px is not too close to 0. Here you see already that you have some conditions. This small here is implying smoothness. And also px not being close to 0 is also implying that you are not going to have these divergences, which you're going to see because you have a natural logarithm of square root of p. If you look at the first order here. And here you have something that is dividing by p. So if p is very, very small, you're going to get into trouble. Now, what we use is we're going to consider an approximation. So we're going to say that S is equal to S0 plus H bar S1. And if we use that, we're going to have that our psi x is going to be A E I H bar S X, and substituting this is E A I E H bar S naught plus H bar S1. So this is going to give me that if you have, so far we have considered an oscillating function to make our assumptions and everything. So in the classically allowed region, which is what we have been using so far, we're going to have psi x A. I'm just substituting now the results that we had, plus minus I divided by H bar x gx dash p x dash. Here we have E minus natural logarithm of px. And then here we have some plus some constants, okay? Not including it, but we do have it. I'll put it. It's nice that you see a few things. E, I see. Okay. So this means that our psi x can be written as AEIC. Now you have this minus E natural logarithm of px, so this is going to give you this. And you're going to have E plus minus I over h bar integral over x dx dash px dash. So this is nice. And we have come to some solution actually we can use in practice. You see, this is an approximation for our wave function up to first order in h bar for our s. And if we write this, the general wave function in this region, for the classical allowed region, make it in blue, looks nicer. General Wkb wave function. And let me specify here, classically allowed region, going to have psi x a p square root of px e I divided by h bar px dash gx dash plus b square root of px e to the minus px dash gx dash. So this is nice. We have a solution. And by an analogy which we can make with what we know from a square wave and from these idealized potentials, we can say that this first solution corresponds to a particle moving in the positive direction, meaning growing values of x. And here we have a particle moving in the negative direction. This is something you can see, for instance, already at the beginning here, you had this plus minus. And this came from the solution that you find for s to the 0th order. And what you find then is that obviously, if you want to make it the most general possible solution that you have, you need to consider both possibilities, the plus and the minus. And that's what we have done. We have these two arbitrary constants. And here we consider that we have this situation and this situation. And what we have now is something which goes to first order in H. So loose interpretation and let's put emphasis on loose. Okay, loose interpretation. Px momentum. So when I said, okay, if you take low powers of h bar or even 0th power of h bar, you can relate quantum quantities to classical ones. This is a very good example, but this is loose, right? And this gives you psi x, if you take the modulo square, is going to be, so this is inversely proportional to the particle's velocity. And the phase integrals that you see, they are a generalization of the plane wave behavior that you know. From the square well. Interestingly, also this S that we have can also be related to the classical action, and many of you probably have heard of the classical action. So you can see this from this integral here, which again reinforces this aspect of a classical quantum correspondence if you have low powers of h bar. Now let's see the classically forbidden region. So for this we need E smaller than Vx, and in this case Px, which is given by 2me minus Vx square root, becomes imaginary. This is clear because this here is going to be negative. So you're going to have the square root of a negative number, which then is going to be imaginary. And for that reason, it is convenient to consider Qx, which is then 2m v square root of Vx minus E. So what you have is you're going to have that this is IPX, right? Yep. So this gives psi x, c square root of qx. Remember, c is an arbitrary constant. And then you have plus qx dash gx dash h bar going to x plus g qx square root of qs e minus x qx dash gx dash h bar. Okay, so similarly to the idealized case, similarly to the idealized case, there is growth and decay. So you have one expression here that is going to grow exponentially and the other one is going to decay. So what you can really see is that there are many connections with what we have learned from the idealized step function potentials, and that you can actually link these to the solutions that we are finding. And we discussed regions for which this WKB works, right? We made quite a few approximations, quite a few assumptions, and the next clip will discuss what to do in regions in which it doesn't work, okay? So thank you for watching, and see you soon.